Building a global video platform from the ground up is one of the most punishing system design challenges in software engineering. You are dealing with a staggering volume of data, measured in petabytes, that has to be moved, stored, and served seamlessly to billions of active users. If you attempt to handle this load using a standard monolithic architecture, where one centralized server handles all incoming traffic, the system collapses almost immediately. A single massive file upload eats up available memory and connection threads and crushes the server under its own weight. This failure reveals the core paradox of a video streaming platform. The architecture must simultaneously serve two completely conflicting sets of users. On one side, you have content creators. They are uploading massive, multi-gigabyte binary files, often over unstable or slow network connections. These uploads take time and require persistent, heavy data transfers. On the other side, you have the viewers. They demand instant, sub-second, buffer-free playback of those exact same files. In a traditional synchronous system, a request holds a connection open until the task is complete. When a creator uploads a 4-gigabyte video, that HTTP request monopolizes a slot in the API server's connection pool for minutes or even hours, eventually timing out. Multiply that by thousands of simultaneous uploads, and the server's connection pool is exhausted. The heavy, long-running upload tasks block all the lightweight read requests from viewers trying to load the homepage. The entire site effectively goes offline. To achieve hyperscale, you have to abandon synchronous design entirely. The system must be physically and logically decoupled into 3 strictly isolated domains: an ingestion plane for uploads, a metadata plane for data, and a delivery plane for streaming. The first architectural shift happens right at the front door. We bypass the main API server entirely for video uploads. Instead, the client application requests a secure, pre-signed URL and writes the heavy binary chunks directly into original object storage. These uploads are broken down into small chunks. If a user's internet connection drops halfway through a 5-gigabyte transfer, the client only needs to retry the failed chunk rather than starting the upload from scratch. Once that raw file lands in storage, it is completely useless to viewers. It has to be transcoded into dozens of different streaming formats, optimized for different screen resolutions, and compressed using efficient codecs like H.264 or AV1. To manage this massive processing load without slowing down the user experience, we introduce an asynchronous message queue, like Apache Kafka. The moment the final chunk hits object storage, the upload service instantly returns a success response to the creator. Behind the scenes, it silently drops a processing event into the Kafka queue for the backend workers to pick up whenever they have capacity. The backend job orchestrator uses a directed acyclic graph, or DAG, to break the video into a parallel workflow. Instead of one server churning sequentially, distinct transcoding server workers encode the 1080p, 720p, and audio tracks simultaneously. The output of this process is a collection of thousands of tiny video segments and a text-based manifest file. These are deposited into a completely separate bucket called transcoded object storage. By pushing the heaviest compute operations into a fleet of asynchronous background workers, the user-facing upload API remains lightning fast and immune to processing gridlock. While the binary video files are stored safely in object storage, we have to handle the lightweight, high-velocity data, user profiles, video titles, and engagement metrics like views and likes. When scaling databases, there is a common trap. Many engineers assume you can solve a database bottleneck simply by upgrading the hardware to a more powerful machine, or by adding read replicas. This comparison shows the limits of scaling. Vertical scaling hits hardware maximums. Horizontal scaling distributes load across smaller servers. Read replicas also fall short here. A platform generates massive write throughput, and in a replicated setup, writes still bottleneck at one primary master. The definitive solution for this high-velocity data is horizontal sharding. You take the massive, overloaded database and partition it into smaller, completely independent database machines. This diagram shows the partitioning strategy. A hash function, taking the user ID modulo 4, dictates which of the 4 shards stores the data. By routing using a partition key, all of a creator's metadata lives on the exact same shard, avoiding slow cross-shard queries. However, sharding introduces a dangerous architectural hazard known as the celebrity hotspot. If a massive, globally viral video is uploaded, millions of concurrent reads will hit the exact same shard it happens to live on, overwhelming that specific machine while the others sit idle. To protect the shards, targeted in-memory caching layers, like Redis, are placed directly in front of the database. These caches absorb the massive viral read spikes, serving the data from RAM before the request ever reaches the physical database disk. Sharding allows write capacity to scale linearly with the number of nodes in the cluster. But physically fragmenting your database creates a massive new problem. How do you search for a specific video if you no longer know which server it lives on? Users expect that the exact second a video is published or a title is updated, that content becomes instantly available in the global search bar. You cannot run complex, fuzzy text search queries directly against your operational database shards. Scanning millions of rows across multiple distributed machines for a partial text match will bring your transactional processing to an absolute halt. The traditional enterprise solution, running massive batch jobs every night to re-index the data, is completely unacceptable for a modern platform where relevance is measured in seconds. The modern mechanism for real-time synchronization is a Change Data Capture Pipeline, or CDC. A CDC tool silently reads the database's write-ahead log, capturing changes without adding CPU load. When a title is edited, the tool emits a discrete event into a Kafka stream. A processor transforms it into JSON, pushing it into an Elasticsearch cluster. Change Data Capture enables sub-second global search updates, ensuring viewers can find new content instantly without placing any analytical query load on the primary databases. With the data indexed and the files processed, we reach the final architectural hurdle, delivering those massive transcoded video segments to 1 billion daily viewers. This diagram shows the delivery flow bypassing API servers for streaming. Instead, a global CDN replicates video chunks to thousands of edge servers. A user in Tokyo pulls data locally, rather than waiting for packets from Virginia. While server placement is critical, scalability relies on a reversal of logic. The massive backend servers and CDN edge nodes remain stateless and simple, while the actual streaming intelligence is pushed into the user's own video player. This client-side intelligence is driven by a protocol called Adaptive Bitrate Streaming, or ABR. An ABR stream manifest outlines video quality tracks, 1080p, 720p, and 480p, broken into segments. During playback, the client monitors network throughput and its playback buffer. If bandwidth drops, the player pivots, requesting the next segment from the 480p track instead of 1080p. This dynamic switching logic heavily favors continuous playback over maximum visual quality. By adapting to the network in real time, the client effectively eliminates the dreaded buffering wheel. Maintaining petabyte scale requires aggressive decoupling of ingestion from delivery, sharding asynchronous data pipelines, offloading complex computational logic to the user's own device.